Hi all, we are at the brim of our CBSE board exam and now we are here to discuss some important questions from chemistry. Let us start with some numericals from electrochemistry. Okay, let us move on to the questions, okay?
Sure.
The first question is, calculate the EMF of the cell and the standard electropotential of the cell is 1.05 volt. Nickel plus 2 Ag plus gives Ni2 plus 2 Ag. You can see the concentration is given in the bracket and you are asked to find what? You are asked to find the EMF. Okay, here in this question, we are asked to find the EMF. Look, here's the formula to find the EMF. That is EMF of the cell is equal to standard electropotential of the cell minus 0.0591 by N log concentration of anode by concentration of cathode. And you know, now here our anode is nickel and cathode is silver here. And I'm going to substitute all these values. For the standard electropotential, our value is 1.05 volt. So let us look at that 1.05 minus 0.0591 by N. N is the charge of the ion. It's 2 here. So I'm writing this 2 log concentration of anode. Anode is nickel. And in the question you can see the concentration is 0.160. So 0 log 0.160 by concentration of cathode. Cathode is silver. That is about 0.002. And you can see here 2 silver is there. So I'm going to put a 2 here, the whole square. On substitution, 1.05 minus 0.0591 by 2, you get 0.0295 into log. And when you go for the substitution, you get this 40,000 here. Now, just do the calculation. You will automatically come to the answer, that is 0.91 volt. Is it clear? I think it's clear for you. Okay.
Now let us move on to second question. Here in the screen you can see the reaction 2Cr plus 3Cd2 plus gives 2Cr3 plus 3Cd. That means here we have electrode, standard electrode potential at cathode is equal to minus 0.40 and standard electrode potential at anode is equal to minus 0.74. Here we have to calculate standard electrode potential. That is our first question. So we know the formula standard electrode potential of the cell is equal to standard electrode potential at cathode minus standard electrode potential at anode. So let us substitute the values which are given here. So first we know that E0 cathode, that is standard electrode potential at cathode, is negative 0.40 minus we have standard electrode potential at anode is negative 0.74. So here you are getting negative 0.40, negative into negative we know it is positive, so 0.74. So by calculating we are getting positive value 0.34 volt. That is our answer for first question. Now let us move on to second question. Here second question they have asked change in Gibbs free energy. So here we know that delta G is equal to negative N F E0, and we know that here N is the number of electrons transferred. In this case N is equal to 6. You can calculate from the reaction. So by substituting the value for N as 6 into F value is 96,500, we all know that, into E0 value we just calculated, substitute that value also. Then finally we will get the answer negative 1.968 into 10 raised to 5. The unit of Gibbs free energy, change in Gibbs free energy is joule per mole. Similarly, we will do third question. Third question they have asked Kc, that is equilibrium constant. In this case, I am writing here. We know the formula log Kc is equal to N into E0 cell divided by 0.0591. See here we have to calculate Kc. So we have to substitute all the values because we know the value of N, we know the value of E0 cell, okay, and thereby we will be getting log Kc value. And how to find this Kc value? We can take anti-log of this value, then we will get Kc value, that is 3.16 into 10 raised to 34. This is the answer we are getting for third sub question. Is that clear? Okay, ma'am, now let's go for third question.
Okay. Following reactions may occur at the cathode during the electrolysis of aqueous copper chloride solution using platinum electrodes. Here, there is an equation, that is copper to Cu2 plus 2 electron gives Cu. Then they are provided with electrode potential value like 0.34 volt. Then another reaction is there H plus electron gives H. Here electrode potential value is 0. On the basis of the standard electrode potential values, which reaction is feasible at the cathode and why? Okay, in this question, we know that higher reduction potential means there is more feasible to
The reaction will be feasible.
at cathode. So here, copper in the value തന്നിരിക്കുന്നത് 0.34 volt ആണ്, അതും positive ആണ്. In the case of hydrogen, it is 0. So it's very well clear that the reaction of copper will be feasible at cathode, right? So the correct answer is copper plus 2 electron gives copper. This is the cathode reaction. Okay, clear?
Here we have our fourth question. It's also numerical. The molar conductivity of a 1.5 mole solution of an electrolyte is found to be 138.97 centimeter square per mole. Calculate the conductivity of the solution. Okay, here the concentration is given, it is 1.5 molar. And the molar conductivity is also given, it is 138.9, and you are asked to find the conductivity. You know, conductivity is the reciprocal of resistivity, that is our kappa. We have learned the equation, that is molar conductivity lambda m is equal to kappa into 1000 by C, that is written here. And from this equation, we have to find kappa, that is our resistivity. It's clear from the equation. You can say kappa is equal to molar conductivity lambda m into C by 1000. Just substitute the values, then only you get the answer. Okay, for lambda m, we get 138.9. For concentration, it is 1.5 mole. And 1000, you get the answer 0.20835. You just go for the substitution. You will clearly go to the answer. Okay.
Okay, നമുക്ക് ഇനി അഞ്ചാമത്തെ ക്വസ്റ്റ്യനിലേക്ക് പോകാം. A zinc rod is dipped in 0.1 molar solution of zinc sulphate. The salt is 95% dissociated at this dilution at 298 Kelvin. Calculate the electrode potential value. Okay, here E0 zinc 2 plus by zinc value is minus 0.76 volt. So, നമുക്ക് electrode potential കണ്ടുപിടിക്കാം അല്ലേ? നോക്കിക്കേ, the electrode reaction നമുക്കറിയാം സിങ്കിൻ്റെ കേസിൽ. Okay, zinc 2 plus 2 electron gives zinc. Okay, oxidation reaction ആണ്. Then നമുക്ക് Nernst equation അറിയാം. നോക്കാം, E Zn 2 plus by Zn the equal to standard electrode potential of zinc 2 plus bar zinc minus 0.0591 by 2 log 1 by zinc 2 plus. Okay, then
That is the concentration of zinc 2 plus.
Yes. Zinc concentration of zinc 2 plus ion equal to 95 by 100 into 0.1. So we'll get the answer 0.095. Okay, then is Zn 2 plus bar zinc equal to minus 0.76 minus 0.0295 log 1 by 0.95. Here zinc 2 plus in the value എത്രയാണ്? Concentration 0.095. അവിടെ substitute ചെയ്യുക. So we'll get the final answer like minus 0.79 volt. Okay.
I think the concentration of salt is 95% there. അതുകൊണ്ടാണ് നമ്മൾ 95 by 100 എന്ന് അവിടെ എടുത്തത് അല്ലേ?
And the concentration taken is 0.1.
Multiplied by this 0.1, you get the concentration of Zn2 plus.
Okay.
Okay, I think it's clear.
നമുക്ക് ആറാമത്തെ ക്വസ്റ്റ്യനിലോട്ട് കിടക്കാം.
Calculate the degree of dissociation of acetic acid if its molar conductivity is 39.05 Siemens centimeter square mole inverse. Given limiting molar conductivity value for H plus ion is 349.6 Siemens centimeter square mole inverse, and limiting molar conductivity for CH3COO minus ion is 40.9 Siemens centimeter square mole inverse. അപ്പോൾ we have to calculate the degree of dissociation. Okay, അപ്പോൾ അതിനുള്ള ഇക്വേഷൻ എന്താണ്? That is alpha equal to lambda m bar lambda m0. That is limiting molar conductivity of acetic acid. Okay, അപ്പോൾ acetic acid എങ്ങനെയാണ് സ്പ്ലിറ്റ് ആവുന്നത്? നോക്കിക്കേ, ലാംഡ 0 CH3COH നമുക്ക് എങ്ങനെ കാൽക്കുലേറ്റ് ചെയ്യാം? ലാംഡ 0 H പ്ലസ് ലാംഡ 0 CH3COO മൈനസ്. ഓക്കെ, ദെൻ ഇവിടെ വാല്യൂസ് തന്നിട്ടുണ്ട്, അപ്പോൾ നമ്മളത് അപ്ലൈ ചെയ്താൽ മതി അല്ലേ, സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്യുക. ദെൻ എന്ത് ചെയ്യും, നമുക്ക് ലാംഡ 0 എം വാല്യൂ കിട്ടും. ദെൻ എന്ത് ചെയ്യും, ആൽഫ നമുക്ക് കണ്ടുപിടിക്കാം. ദാറ്റ് ഈസ് ലാംഡ എം ബാർ ലാംഡ 0 എം ചെയ്യുക. സോ വിൽ ഗെറ്റ് 0.1 is the answer for alpha. Okay, that is a dissociation, degree of dissociation. Okay, clear?
Now we have some questions from surface chemistry. It's a very important chapter, you know. First one, based on the Hardy-Schulze rule, explain why the coagulating power of phosphate ion is higher than chloride. You know, phosphate is PO4 3 minus, its valency is 3, and for chloride is Cl minus. And according to Hardy-Schulze rule, the coagulating power of the electron depends on its flocculating valency. Okay, now according to Hardy-Schulze law, electrolyte coagulation properties depend on the valency of the coagulating ion. The higher the charge in flocculating ion, smaller is the amount of electrolyte required. You know, phosphate valency is 3 and chloride is 1. So obviously phosphate has more valency, so it will have more coagulating power. So we can say the coagulating power of phosphate is higher than chloride. Okay. Now, okay, Sangeeta ma'am, let us move on to the next question.
Yes, sure. See, അടുത്ത question നമുക്ക് നോക്കാം. How are the following colloids different from others with respect to of their dispersion medium and dispersed phase? Give one example of each. So we are familiar with these terms, right? Dispersion medium and dispersed phase in our concept colloid. So here they have given the questions regarding aerosol. Okay, let us take some example. Aerosol. In the case of aerosol, let us write the dispersed phase. So here, first in the case of aerosol, the dispersed phase is solid, where this solid is mixed with dispersion medium, that is gas. Okay, and we can take an example. What is the example for this aerosol? It is smoke and dust. These are some examples. We can add some more examples. Okay, and second one, emulsion. In the second case, here dispersed phase is liquid. In here, liquid is dispersed in liquid dispersion medium. So note down the dispersed phase as well as dispersion medium for individual case. So first we have discussed for aerosol. The second one is emulsion. Okay, example is cod liver oil. Here dispersed phase as well as dispersion medium is liquid. And in the third case, hydrosol. In the case of hydrosol, here dispersed phase is solid and dispersion medium is water. And example is starch dispersed in water. Okay, I think it's understood. Now next one, we'll move on to third question.
Okay, describe a chemical method each for the preparation of the salts of sulphur and platinum in water. ഇപ്പോൾ സൾഫറിൻ്റെയും പ്ലാറ്റിനത്തിൻ്റെയും സോൾ നമുക്ക് പ്രിപ്പയർ ചെയ്യാം. ഇപ്പോൾ സൾഫറിൻ്റെ സോൾ എങ്ങനെയായിരിക്കും പ്രിപ്പയർ ചെയ്യുന്നത്?
Oxidation of hydrogen sulfide
in presence of nitric acid. ഓക്കെ, അങ്ങനെ നമുക്ക് സൾഫറിൻ്റെ സോൾ പ്രിപ്പയർ ചെയ്യാം. പക്ഷെ അതുപോലെ തന്നെ പ്ലാറ്റിനത്തിൻ്റെ സോൾ പ്രിപ്പയർ ചെയ്യാനായിട്ട് ഒരു ഇമ്പോർട്ടൻറ്റ് മെത്തേഡ് ഉണ്ട്. അതാണ് ബ്രെഡിക്സാക്ക് മെത്തേഡ്. അപ്പോൾ ആ മെത്തേഡ് പ്രകാരം 2 പ്ലാറ്റിനത്തിൻ്റെ മെറ്റാലിക് ഇലക്ട്രോഡ്സ് എടുക്കുക, അതിന് ഒരു ഡിസ്പേർഷൻ മീഡിയത്തിൽ നമ്മൾ ഡിപ്പ് ചെയ്ത് വെക്കും. ദെൻ എന്ത് ചെയ്യും, അതിനൊരു വോൾട്ട് മീറ്റർ ആയിട്ട് കണക്ട് ചെയ്യും. ദെൻ കറണ്ട് പാസ് ചെയ്യുമ്പോൾ ഓഫ് കോഴ്സ് അവിടെ എന്ത് ചെയ്യും, ഈ പ്ലാറ്റിനം ഇലക്ട്രോഡിൽ വേപ്പേഴ്സ് ഫോം ചെയ്യും അല്ലേ, അതിന് വേപ്പറൈസ്ഡ് ഫോമിലേക്ക് മാറും. അപ്പോൾ നമ്മളിതൊരു ഐസ് ബാത്തിലാണ് ഇത് നമ്മൾ സെറ്റ് ചെയ്യുന്നത്. അപ്പോൾ ഓട്ടോമാറ്റിക്കലി അവിടെ കണ്ടൻസേഷൻ നടക്കും. ഈ കണ്ടൻസ്ഡ് ആയിട്ടുള്ള പാർട്ടിക്കിൾസിന് കൊളോയിഡൽ പാർട്ടിക്കിൾസിൻ്റെ സെയിം സൈസ് ആയിരിക്കും. അപ്പോൾ നമുക്ക് പ്ലാറ്റിനത്തിൻ്റെ സോൾ അങ്ങനെ പ്രിപ്പയർ ചെയ്യാം. ഇതാണ് ആക്ച്വലി ബ്രെഡിക്സാക്ക് മെത്തേഡ് വഴി നമ്മൾ ചെയ്യുന്നത്.
അപ്പോൾ ഡിസ്പേർഷൻ മീഡിയത്തിൽ ആ പ്ലാറ്റിനം വേപ്പേഴ്സ് വിൽ ഗെറ്റ് കണ്ടൻസ്ഡ് ഇൻ കൊളോയിഡൽ സൈസ് അല്ലേ, അങ്ങനെയാണ് പ്ലാറ്റിനം സോൾ പ്രിപ്പയർ ചെയ്യുന്നത്. ഓക്കെ, ദാറ്റ് ഈസ് ബ്രെഡിക്സാക്ക്.
Okay, then നമുക്ക് അടുത്ത ക്വസ്റ്റ്യൻ നോക്കാം അല്ലേ.
Now here we have the fourth question. That is, write the dispersed phase and dispersion medium of dust. You know, in dust, it's a very simple question. In dust, the dispersed phase is solid and the dispersion medium is air. And to the second part, a colloidal sol is prepared by the method given in the figure. What is the charge of silver iodide colloidal particles formed in the test tube and how this sol is represented? So here, when potassium iodide is added to silver nitrate solution, you know silver nitrate is the dispersion medium there, and you get the silver and iodine reactive form. Silver iodide is the precipitate, and potassium KNO3 is also formed. Okay. Now, this silver iodide is the precipitate there. It will, from the dispersion medium, you can see dispersion medium is silver nitrate and our precipitate is silver iodide, and the common ion is silver here. Common ion is silver. So what happens? The silver iodide will selectively absorb silver Ag plus from the dispersion medium. So the colloid will become positively charged. That's our answer. Okay. So now let us move to the answer. When potassium iodide solution is added to silver nitrate, a positively charged sol result due to the adsorption of Ag plus ions from the dispersion medium. That's it. Now we have also a second question here. Why is physisorption reversible whereas chemisorption is irreversible? Why is physisorption reversible? Because the physisorption arises because of the weak van der Waals forces between the dispersed phase and the dispersion medium. That is given here. Physisorption arises because of the weak van der Waals force between the adsorbate and the adsorbent. Hence, that can be reversed on the application of bigger forces. But chemisorption occurs due to chemical reaction between two molecules. So we cannot reverse it. That's it. Now, let us, okay, Sangeeta ma'am, let us move on to the next question. Okay.
So here we can see fifth question, define the following terms. So these are direct question, very important also. Here the first one, lyophilic colloid. You are all familiar with these terms, lyophilic and lyophobic colloid. Here we are going to discuss about lyophilic colloid. So what do you mean by lyophilic colloid? The colloidal solution in which particles of dispersed phase have a strong affinity for dispersion medium. So there will be a strong affinity for this dispersed phase towards dispersion medium. That is why it is called lyophilic. That means more loving towards this dispersed phase is more loving towards dispersion medium. Okay. These colloids, even if precipitated, change back to colloidal form simply by adding dispersion medium. So, lyophilic sols are reversible also. Okay. Examples are glucose, starch rubber, etc. Now we have zeta potential. That is the second question. Move on to the second question.
Zeta potential is the difference in potential between the fixed layer and diffuse layer of a colloidal sol. That is, I told you, in the previous question, I told you, the silver iodide precipitate, it absorbs the silver ions. So, a positively charged layer will be formed around this precipitate like this. So, obviously, a negative charged layer, that is of I minus, will also form around this like this. Okay, this positively charged layer, this is called the fixed layer. And this negatively charged layer is called the diffuse layer. There is a potential difference between these layers, and that is called our zeta potential. That is the difference in potential between the fixed layer and the diffuse layer of a colloidal sol is called a zeta potential. Now, moving to the next question, that is our associated colloid.
Okay, what do you mean by associated colloid? Here, the substances which at low concentration behave as normal strong electrolytes but at higher concentration exhibit colloidal behavior due to the formation of aggregated particles. So here, associated colloid in the varnal, it is also called micelles. Okay, and see here actually what is this associated colloid? Here these colloid forms together like a group. That is why it is called associated colloid. And when it is occurring, actually, we have a temperature above which these micelles are forming. And that temperature is called Kraft temperature. And above a particular concentration, so note down this term, critical micelle concentration. That is CMC. Example for these are surface active agents such as soap and synthetic detergents. So these are important questions. Let's move on to next question.
Out of magnesium chloride and aluminum chloride, which one is more effective in causing coagulation of negatively charged salt and why? Okay, this is our first question. So, according to Hardy's Schulze rule, the negatively charged salts.
Magnesium chloride, I think the valency is plus 2. And
aluminum
chloride
chloride
is plus 3. So, according to Hardy-Schulze rule, the more the valency, the more will be the coagulating power. So, magnesium and aluminum chloride, valency cool aluminum obviously air has plus 3 charge and magnesium has only plus 2 charge. So, the more effective coagulation will be for aluminum chloride, the AICI3.
So, the coagulating power is always aluminum chloride.
More for aluminum chloride.
That is it.
Okay. And second question, out of sulfur, salt and proteins, which one forms multimolecular colloids? നമുക്കറിയാം സൾഫറിന്റെ മോളിക്യൂൾസ് വളരെ സ്മോൾ ആണ് കമ്പയർ ടു പ്രോട്ടീൻസ്. പ്രോട്ടീൻസ് ആർ മാക്രോമോളിക്യൂൾസ്. ഓക്കെ, സോ എപ്പോഴും മൾട്ടി മോളിക്കുലർ സ്പീച്ച് കൊളോയിഡ്സ് ഫോം ചെയ്യുന്നത് ആര് തന്നെയായിരിക്കും?
സൾഫർ ആയിരിക്കും.
ഓക്കെ. ആൻഡ് തേർഡ് ക്വസ്റ്റ്യൻ, leather gets hardened after tanning. Explain. And the third question is explain. നമുക്കറിയാം ലെതർ എന്ന് പറയുന്നത് പോസിറ്റീവ്ലി ചാർജ്ഡ് ആയിട്ടുള്ള കൊളോയിഡ് ആണ്. Then tanning consists of negatively charged colloidal particles. So when they are mixed or when a hide is soaked in tanning, the mutual coagulation takes place and
leather gets hardened.
And as a result, leather gets hardened.
Hide is same, animal skin.
Okay. Clear.
Now it's D and F block elements. Let us move on to the next chapter, that is our D and F block elements, and our first question is, although fluorine is more electronegative than oxygen, the highest fluoride of Mn is MnF4, whereas the highest oxide is Mn2O7. Give reason. That is the question. Here in MnF4, fluorine have a -1 charge. So 4 fluorine means -4 state, and therefore manganese have a plus 4 oxidation state. And in Mn2O7, you can see one oxygen is -2. So 7 oxygen obviously will be -14. So for 2 manganese, it comes to be plus 7. So you can say in these MnF4 and Mn2O7, fluorine is more electronegative than oxygen, but the oxidation state of manganese in oxide is more than fluorine. Why? Because fluorine forms only single bond with metals, whereas oxygen forms multiple bonds with metals. That is why this happens. That's it. Okay, Sangeeta ma'am, let us move on to the very next question.
Here you can see, although +3 oxidation state is the characteristic oxidation state of lanthanoids, but cerium shows +4 oxidation state. Why? See, in most of the cases, we are explaining the stability based on the electronic configuration or the electrons that are filled in the orbitals, right? In this case, we have given electronic configuration of cerium is, you can see noble gas xenon is referred here. Then we have outermost electronic configuration 4f2, 5d0, 6s2. In the case of cerium 4+, Ce4+, that means 4 electrons are losing from outermost orbital, and here we are getting xenon, then we are having 4f0, and you all know that it is attaining a noble gas configuration, thereby it has a tendency to attain such oxidation state. Okay, so this is the answer. Now move on to next question, third one.
Okay, third question is, explain the following observations. Transition elements generally form colored compounds. Zinc is not regarded as transition metal. Okay, transition elements. We all know that transition elements are starting from, in the periodic table, is 3 to 12. Right?
Group 3 to 12.
Group 3 to 12. So, because of the presence of unpaired d electrons, it shows dd transition. So, that's why it shows colored compounds. Okay, and in the case of zinc is not regarded as transition metal. Why?
Because transition elements have a incompletely filled d orbitals.
But zinc is having electronic configurations 4s2, 3d10.
That is completely filled d orbital.
That is why.
So because of that, zinc is not considered as
transition metal.
Yeah, transition element.
Okay.
So let's move on to next question, ma'am.
Now we have another question. Which metal in the first transition series, that is 3D series, exhibits +1 oxidation state most frequently and why? Our answer is copper exhibit +1 oxidation state more frequently. So the atomic number of copper is 29.
20.
So it has an electronic configuration of 3d10 4s1. Now if it loses one electron, it will have a 3d10 configuration. That is, it becomes stable. That is why copper frequently shows +1 oxidation state.
Because of fully filled d
Because it
orbitals.
has a fully filled d orbital then. So it attains stability.
Okay, now let's move on to fifth question in this lesson. Which of the following cations are colored in aqueous solutions and why? So in the previous question, we have seen that if there are unpaired electrons in d orbital, that metals will be having colored nature, right?
It is because
so in
of
this
DD transition.
DD transition. Here we have, according to crystal field theory, we have studied in our coordination compound lesson. So recall that topic here. So in this case, scandium 3+. Let us recall the atomic number. Scandium is 21. So what is the electronic configuration in this case? We have 3D, 2 and 4s1. And so here scandium നോക്കുവാണെങ്കിൽ നമുക്ക് outermost electronic configuration വരുന്നത് 3D1 4s2. Okay, so I'm referring outermost electronic configuration because they are imparting the color nature. Okay, they are deciding the color nature of the metal ion. Okay, in this case, scandium 3+ means they are losing 3 electrons. See, here we are having only 3 electrons. 2 electrons are from 4s and 1 electron from 3d. Okay, so after removing this, we are not having unpaired electrons. So that is why scandium 3+ is not imparting color nature. And similarly, we can explain the same logic for following metal ions. See, vanadium 3+. In this case, we have 2 unpaired electrons. Refer the outer electronic configuration. And in titanium 4+, we are not having unpaired electrons. So it is colorless. Then Mn2+, we are having 5 unpaired electrons. So we can conclude that vanadium 3+ and manganese 2+ are colored in their aqueous solutions due to presence of these unpaired electrons. Okay, move on to next question.
Sixth question. Actinoid contraction is greater than lanthanoid contraction. Give reasons. Okay, answer is this is due to weaker shielding by 5f electron in actinoids as compared to shielding by 4f electrons in lanthanoids. അപ്പോൾ എഫ് ഓർബിറ്റൽസിൽ പ്രസന്റ് ആയിട്ടുള്ള ഇലക്ട്രോൺസിന് ഷീൽഡിംഗ് എഫക്റ്റ് കമ്പാരിറ്റീവ്ലി കുറവാണ്. അപ്പോൾ ആക്ടിനോയിഡ്സിന്റെ കേസിൽ 5f ഇലക്ട്രോൺസ് ആണ്, ലാന്തനോയിഡ്സിന്റെ കേസിൽ 4f ആണ് ഉള്ളത്.
അപ്പോൾ ആക്ടിനോയിഡ്സിലെ എഫക്റ്റീവ് ന്യൂക്ലിയർ ചാർജ് will be greater. So that is why actinoid contraction is greater than lanthanoid contraction. Yeah.
Okay.
Now here comes our seventh question. How do you account for the following? The first one is the third ionization enthalpy of manganese, that is atomic number 25, is exceptionally high. Let us look at the answer. The third ionization enthalpy of manganese is very high because the third electrons has to be removed from the stable half-filled 3d orbital. Look here, Mn2+ have an electronic configuration of 3d5. That is, it is partially filled, so it has a stable configuration. So to remove an electron from a stable orbital is very difficult. That is why the third ionization enthalpy of manganese is exceptionally very high because it is already stable in the +2 state. So now need to go to the +3 state. If it wants to go there, a very high energy is needed.
You all know, you all familiar with this term, right? Ionization enthalpy. It is the energy to remove the outermost bonded electron in the gaseous neutral state of an element. So here third ionization enthalpy is very high, as ma'am explained. Now move on to next one.
There is the name a transition element which does not exhibit variable oxidation state. That is, it's a scandium. Atomic number 21. That does not exhibit a variable oxidation state. Scandium does not show a variable oxidation state.
So move on to 8th question. Calculate the magnetic moment of Cu2+ on the basis of spin only formula. Here we are referring the formula mu is equal to root of n into n plus 2. Bohr magneton, that is our unit. And n is number of unpaired electrons. So here question is asked regarding copper, right? We know that atomic number of copper is 29 and we know as we have discussed earlier also, the electronic configuration of copper, right? 3d10,
4s1.
4s1, that is the outermost electronic configuration. So after losing 2 electrons, that is from 4s1 and 3d10, we are getting 3d9. So by representing this box representation, we can see how many unpaired electrons are there. See, 5 electrons are filled, then pairing taking place. So here we are having only 1 unpaired electron. So substitute the value of this 1 in the place of n, then we will get this value. Mu is equal to root of 1 into 1 plus 2, that is 1.73 Bohr magneton.
Okay, നമുക്ക് അടുത്ത amines എന്നുള്ള ചാപ്റ്ററിലെ ക്വസ്റ്റ്യൻസ് നോക്കിയാലോ.
That is, aniline is a weaker base than cyclohexylamine. Explain. You know, in aniline, benzene NH2 group is directly attached to our benzene ring. So, here you can see that benzene ring will act like an electron withdrawing group. Okay, that is the negative charge, the electrons on nitrogen is delocalized over this benzene ring. You can see here the electrons from this, the lone pair electrons on nitrogen, it will come to here, and the double bond electrode come to this position. So you get this carbon, we form a double bond here, and we get a negative charge here, and this nitrogen will get a positive charge. That is, the electrons in the nitrogen is delocalized over the ring, so it is not available for donation. Okay, but in case of the cyclohexylamine, there is no such things happen. There is no resonance structure. The nitrogen has these lone pair electrons with it. So
they will act as.
So that is why we can say, let us look on to the answer. Because of resonance, the lone pair on nitrogen is attracted by the benzene ring, and donor tendency of lone pair of electrons of NH2 group decreases. But there is no resonance in cyclohexylamine. Thereby, the lone pair present on nitrogen is freely available for donation. That is it. Clear? Let us move on to our next question. That is,
write the structures of main products when aniline reacts with the following reagents. So these are direct questions we are studying in this chapter. So first you can see, when aniline reacts with bromine, okay, you can see we'll get 2,4,6 tribromoaniline plus 3HBr, hydrogen bromide. So here we are getting 2,4,6 tribromoaniline, and in the second case, when this aniline reacts with hydrogen chloride, see here what happens, this hydrogen chloride splits into H plus and Cl minus, and it will go towards this NH2 group, and here you can see formation of NH3 plus, then Cl minus. Here this H plus and Cl minus will join together with this NH2, then we will get anilinium chloride. And the third one, you can see aniline reacts with acetic anhydride with pyridine, also with pyridine. Here you can see this O actually should lie here. Okay, then we'll get the answer acetanilide. Okay, here what is happening, in the presence of NH2, okay, in the place of NH2 hydrogen is going, and in the place of that CH3CO is bonded. Okay, that is why we are getting acetanilide. So these are the direct questions we have from this chapter. Now let us move on to next question.
that is, the correct order of increasing boiling point for the bases CH3NH2, that is our methanamine, CH3 the whole twice NH, that is dimethyl, it's not dimethylamine actually, I am not mentioning about the IUPAC name here, CH3 the whole twice NH and CH3 the whole thrice N. We have to arrange them in order of their increasing boiling point. As you know, CH3 the whole CH3 NH2, it is a primary amine. And CH3 the whole twice NH, it's a secondary amine. And CH3 the whole thrice N, it is a tertiary amine. And here boiling point factor depends on the hydrogen, intermolecular hydrogen bonding. As you can see, this primary amine has hydrogen present in it. So it has more intermolecular hydrogen bonding than secondary. So obviously, the boiling point of primary amines will be more than secondary. But in case of tertiary, there is no hydrogen there, so there is no chance of hydrogen bonding. So no hydrogen bonding takes place and boiling point will be less. So our order will be tertiary less than secondary less than primary. You have to study like this. You have to approach these type of questions like this. Okay, when you are asked to arrange them in order of the increasing boiling point, you have to look at the primary, secondary, and tertiary cases. Okay, that is it.
Okay, now let us discuss on the next question. Describe Hinsberg test for differentiation of primary, secondary and tertiary amines, give the chemical equation.
It's a very, very important question. That is a test to distinguish between our primary, secondary and tertiary amine. You know this Hinsberg reagent, that is benzene sulfonyl chloride, that is C6H5SO2Cl. That is called our Hinsberg reagent. Now let us look at the reaction of this Hinsberg reagent. That is, this is our C6H5SO2Cl with our primary amine. You know, this is a C2H5NH2. That is our ethanamine. It's our primary amine. Always recall this Hinsberg reagent treating this primary amine. What happens here? You can see this Cl and H goes on like this, like HCl. And this nitrogen gets connected to the sulfur and you get a product like this. And now you can see the nitrogen has a hydrogen here. This hydrogen is acidic. This hydrogen is acidic. So this product, it is soluble in alkali. So always remember, when a benzene sulfonyl chloride reacts with an amine and it forms a salt, and if this salt is soluble in an alkali, then surely it is a primary amine. Okay, but what happens if it is a secondary amine? Look here, this is a secondary amine. That is C6H5 the whole twice NH. As is the NH, it's a secondary amine. Now here also the same thing happens. This H and Cl react to form HCl. It goes on like that, and this nitrogen will get connected to this sulfur. You get a product like this. Now here you can see there is no hydrogen on this nitrogen. There is no acidic hydrogen there. So what happens? This salt is formed, but this salt is insoluble in an alkali. Okay. So when a amine reacts with a Hinsberg reagent and forms a salt, but if it is not soluble in an alkali, surely it is a secondary amine. And for tertiary amine, there is no reaction. It is a very, very important reaction. So always remember this.
Here we have a question from the chapter Coordination Chemistry. What is meant by chelate effect? എന്താണ് chelate effect എന്ന് നോക്കാം. When a bidentate or polydentate ligand uses its two or more donor atom to bind a single metal ion, it is said to be a chelate ligand. The stabilization of a coordination compound due to chelation is called chelate effect. അതായത് ഒരു സിംഗിൾ മെറ്റൽ അയോണിന് ചുറ്റും ബൈഡെൻറ്റേറ്റും അല്ലെങ്കിൽ പോളിഡെൻറ്റേറ്റ് ആയിട്ടുള്ള ലിഗാൻസ് വരുമ്പോൾ എന്ത് ചെയ്യും? അവർ ജോയിൻ ചെയ്യും അല്ലേ? എന്നിട്ട് കെലേറ്റ്സ് ഫോം ചെയ്യും.
They will be more stable.
ഓക്കെ, അപ്പോൾ അതിനൊരു ഇമ്പോർട്ടൻ്റ് ആയിട്ടുള്ള ഒരു എക്സാമ്പിൾ ആണ് EDT. നമുക്ക് അതിന്റെ ഫുൾ ഫോം ഇമ്പോർട്ടൻ്റ് ആണ്. That is ethylene diamine tetraacetic acid. Okay,
and it is a
ഒരു hexadentate ligand. Okay,
now move on to second question. Why are low spin tetrahedral complexes not formed? See here നമുക്ക് ഇവിടെ പറയാനുള്ളത് crystal field splitting. We have to recall that concept. Crystal field splitting taking place in octahedral and tetrahedral complexes. And specifically in tetrahedral complexes, crystal field splitting കുറവായിരിക്കും അല്ലേ? Because of that, electron can easily jump from its ground state to higher excited state. Okay, and see, because of that less crystal field splitting, what we can expect? We can expect lot of unpaired electrons. That is why here this tetrahedral complexes will form high spin complexes. So here question is indirect. See, why are low spin tetrahedral complexes not formed? We already discussed that tetrahedral complexes form high spin complexes. So same reason we can explain. See, low spin tetrahedral complexes are rarely observed because crystal field stabilization energy for tetrahedral complexes is less than pairing energy. So here we can say delta T is less than P, that is pairing energy. Okay, that is why here tetrahedral complexes are forming rarely this low spin complexes. Now let's move on to next question.
Third question is, name the following coordination compounds according to IUPAC system of nomenclature.
So we have certain rules for this, right? So recall that nomenclature rules. So in this case, we have this coordination sphere as cation, okay, and chlorine as anion. So we are naming cation first. That is our rule number 1. And second rule is we are naming this ligand according to its alphabetical order. So let us name this complex tetraamine. Here we are having 4 number of ammonia NH3 group. So tetraamine. Then we are naming aqua, that is H2O. Okay, aqua chlorido, which is a negative ligand. Cobalt is named because it is coming in the cation part. Okay, so cobalt 3 chloride. See here 3 is the oxidation state of this cobalt. How we are getting this 3? So we are calculating from the question. So in the case of first complex, let us see the question here. So here we are having oxidation number, taking it as X, and here we know that 0 is the oxidation state of ammonia, water is also having 0, and chlorine is having -1, and here we are having 2 chlorine ion, okay, chloride ions, Cl. Here we are having -2 charge over this counter ion Cl2. So altogether we are getting x minus 3 is equal to 0, then we are getting x is equal to plus 3. So this 3 is mentioned here. Okay, similarly we can answer the second second complex. Here Cr, Cl2, En twice Cl, and here ligands present as Cl2 and ligands are Cl2 and En twice. So in this case we can name it as dichloroethane 1,2-diamine. Okay, then we are having chromium 3 chloride, and you have to note down this is mentioned in a bracket. Okay, and here also we are getting the oxidation number 3. That is also calculated accordingly. We have calculated in the first complex. Fine. Now let's move on to next question. Fourth one.
Describe the shape and magnetic behavior of the following complexes. That is, the first one is CONH3 the whole 6 3 plus.
So here you can see, we will take the atomic number first. Okay. Atomic number of cobalt. What is the atomic number of cobalt? Here we know it is 27. And what is the electronic configuration? Outermost electronic configuration is 3d7 4s2. But in this complex, the oxidation state of cobalt is plus 3. Okay. So 3 electrons are losing from 4s2. It will go, then we will get 3d6. So we are representing this 6 electrons in the d orbital. So this is our box representation. Okay, here 6 electrons are filled like this. And here you can see ammonia is a strong ligand. It is a strong ligand. So what will happen? And 6 number of ammonia should occupy in the d orbitals of metal ion. So in this case, 6 orbitals should be available, right? And because ammonia is a strong ligand, what will happen? See, we are having empty orbitals also. Let us draw that.
That is a 4s.
Yes, this is our 3d orbitals. This is 4s and 4p. We have studied about the hybridization concept, right? So here electrons are taking place pairing nature. Okay, it will pair up, and here after pairing we will get here these 2 electrons will fill here, and here we will get empty d orbitals, and they are ready to occupy 6 number of ammonia, lone pairs of 6 numbers of ammonia, which is our ligand. So just count the orbitals present. So 1.
I think the hybridization takes place.
Yes, hybridization taking place. So here we are getting D2sp3 hybridization.
So shape is?
So what is the shape of this? We know it is a octahedral complex, right? So shape is octahedral. And magnetic behavior. See, in this case, we are not having the unpaired electrons. So this is diamagnetic in nature. So these are very important questions. So for that, you have to just go through the atomic number and electron filling taking place in the orbitals. So thereby you will get the shape and magnetic behavior. Similarly, we can do for second complex.
Okay. That is NiCN the whole 4 2 minus.
2 minus. And in this case, nickel is having atomic number 28. So similarly, you can just consider.
So I think it is 3d8 4s2.
Here, what will we have to calculate the oxidation state also. So let us see the screen. Here X, and here we are having -4 charge over the CN group and -2 as the counter ion. So let us calculate here. X minus 4 is equal to -2. So here we are getting -2 plus 4 plus 2. So 2 electrons will go from outermost configuration of this nickel. So after that we will get 3d8. Okay. So let us draw here for nickel. This is the box representation. So 8 electrons are filled in d orbitals. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and see cyano group, it is also a strong ligand, and in this case here you can see 4 CN group is going to join, right? So we can see with respect to this coordination number, we can easily explain the shape. Okay. So for magnetic behavior, we have to see the number of unpaired electrons. Fine. So here, because of the presence of Cn, what will happen? Here, this one electron will pair up with this unpaired electron. So it will pair up here, and here we are having the empty orbitals. They are forming dsp2. Here we are getting dsp2 hybridization, which is the hybridization for this square planar. Okay, the shape is square planar here. So with respect to hybridization, we have to identify the shape. Okay, first of all, we will come to know that based on coordination number, we can know that there are two possibilities, square planar and tetrahedral is possible. But with respect to this hybridization, we can confirm that it is having square planar structure. So shape and magnetic behavior is discussed. Okay, now let us move on to next question.
By what test can you distinguish ethanol and benzaldehyde and acetone and acetic acid?
Right, it's a very important question. That is a reaction using as a tolerance test. Using tolerance reagent, tolerance reagent is the ammoniacal silver nitrate solution. The aldehyde usually gives us tolerance test. Okay, when this benzaldehyde, that is our C6H5CH, that is here, benzaldehyde react with our ammoniacal silver nitrate, that is AgNH to the whole twice OH. We get, what will we get? We get benzoic acid. That is what we get here, benzoic acid, and we get a silver mirror. So if we treat an aldehyde with the tolerance reagent, that is ammoniacal silver nitrate solution, you get a silver mirror. So it confirms the presence of an aldehyde. Okay, but tolerance reagent will not give any reaction with ethanol, alcohols. Okay, that is you just generalize as orthoica. It's a very important topic. And our second question is, how will you distinguish between acetone and acetic acid? That is very simple. Acetone and acetic acid, we distinguish by using our sodium carbonate. Okay, Na2CO3. Sodium acetic acid gives a brisk effervescence with sodium carbonate, whereas acetone does not give brisk effervescence. Acetic acid react with sodium carbonate, you get sodium acetate, that is CH3COONA, and you get carbon dioxide and water here. So this is a test used to distinguish between acetic acid and acetone.
Next question.
Okay, ഇവിടെ കുറച്ച് റിയാക്ഷൻസ് പ്രൊവൈഡ് ചെയ്തിട്ടുണ്ട്. ഇതിൽ നിന്ന് അവരുടെ പ്രൊഡക്ട്സ് ഏതൊക്കെയെന്ന് ഐഡന്റിഫൈ ചെയ്യാം. ഓക്കെ, ഫസ്റ്റ് വൺ ഒരു ബെൻസാൽഡിഹൈഡ് ആണ് വിളിക്കുന്നത് അല്ലേ? ബെൻസാൽഡിഹൈഡിനെ കോൺസെൻട്രേറ്റഡ് NaOH വെച്ച് ട്രീറ്റ് ചെയ്യുമ്പോൾ വാട്ട് വിൽ ബി ദ പ്രോഡക്റ്റ്?
Let us look at the answer. Benzaldehyde treated with concentrated NaOH, we get a mix of two products. That is, you get a benzyl alcohol and also sodium benzoate. So that are the products formed when we treat this benzaldehyde with concentrated NaOH. Similarly, another question, that is CH3CO acetyl chloride treated with hydrogen in the presence of palladium or barium sulfate.
It's a reduction.
We get is it a reduction? It's a treating with hydrogen. We get a product A, which on treatment with NH2OH, you get product B. Let us look at this reaction. CH3COCl, that is acetyl chloride. When treated with hydrogen in the presence of palladium and barium sulfate, what you get is the COCl get reduced to CHO. That is, you get ethanol, CH3CHO, which when treated with NH2OH, you get acetaldoxime. That is a CH3CH double bond NOH. That is a product formed.
So here also it is an important one. Aldehyde reacts with hydroxylamine, and here we are getting oxime. Okay, that is also you have to remember.
Now we have another question. Benzene react with acetyl chloride, that is CH3COCl, in the presence of anhydrous aluminum chloride. What will be the product you can give? This is acetophenone. That is C6H5COCH3. That is acetophenone. Okay, that's also a very important reaction. You have to remember that.
Now let us discuss some questions from chemical kinetics. So first one, define activation energy of a reaction. See, here activation energy is minimum extra amount of energy absorbed by the reactant molecules to form activated complex. So before converting to products, these reactants form an activated complex. So the minimum energy required to convert this reactant to activated complex is called activation energy. And in the presence of catalyst, this activation energy gets reduced. Okay, it decreases. The peak of activation energy gets decreased in the presence of catalyst, thereby rate of reaction can be enhanced. Okay, let us move on to next question.
That is, express the rate of the following reaction in terms of the formation of ammonia. That is, we are given an equation N2 plus 3H2 is 2NH3 and you are asked to express the rate. It's very simple question. You know the rate of reaction can be expressed in either the decrease in the concentration of reactant or increase in the concentration of product. So here we have nitrogen and hydrogen as the reactants. So you can write minus d by dt of concentration of N2. That is, the negative sign shows that there is a decrease in the concentration of reactants there. And here also hydrogen, here minus 1 by this stoichiometric value, we take its reciprocal. So minus 1 by 3 into d by dt of concentration of H2 equal to, and here we have the products NH3 the same way. As it is a product, the rate of, there is an increase in the concentration of product. So we get a positive value. That is 1 by 2 into d by dt of concentration of NH3. It's a very simple way to express the rate of a reaction. Always the reactants, we always remember that there's a decrease in concentration of reactant. So give it some negative value. For products, there will be increase in the concentration of product. So give it a positive value. That is all about that.
Now the third question is, a reaction is of second order with respect to a reactant. How will the rate of reaction be affected if the concentration of the reactant is doubled? So let us take first, according to rate law, we know that since it is a second order, we are representing rate is equal to K into concentration of reactant. Suppose A is the reactant, then to the power 2, because it is a second order reaction. For second order reaction, let A, consider it as small letter A. Okay, concentration of A is equal to small letter A. In order to do this value convenient, we are doing this concentration of A as small letter A, and rate will be K into A square. Now, this condition given is, if it is doubled, if the concentration of reactant is doubled, that means here A becomes 2A. That is the condition. So just substitute, instead of A, you have to write this 2A. Then what will happen? Here we are getting 4Ka square. See, 2 square is 4. So 4 times, you can see rate of reaction becomes 4 times. Similarly, we can calculate for if the concentration of reactant reduced to half. That means A becomes A by 2. Substitute here and you will get that rate of reaction will be 1 by 4th. So you have to be very careful while writing the terms given. Okay. Now move on to next question here.
Now we have a numericals here. The rate constant K for a first order reaction has been found to be 2.54 into 10 raised to minus 3 per second. The rate constant K is given. That is, our K is given, and calculate its 3 by 4th life. You are asked to calculate the time. You know the half-life T1 by 2. Likewise, you are asked to calculate 3 by 4th life, and log 4 value is given. And it is clearly mentioned that it's a first order reaction. You know, it's a, for a first order reaction, the time T half is equal to 2.03 by K log 4. So here, substitute the value for K. K is 2.54 into 10 raised to minus 3, and log 4, you will get this value. Just substitute the value, you get 9.09 minutes. It's a very direct question. Okay. This is how we calculate the 3/4 life of a chemical reaction. Now,
okay, next question. Define the following terms. First one, pseudo first order reaction. Second one, half-life period of a reaction. That is T half. Okay, pseudo first order reaction, direct question aanu. Those reactions which are not truly of the first order, but under certain conditions become first order reactions, are called a pseudo first order reaction. Okay, simple aanu. Next, half-life period of a reaction. In the half-life period of a reaction, that means T half. The time taken for half of the reaction to complete. അതായത് ഒരു റിയാക്ഷൻ പകുതി നടക്കാൻ വേണ്ട ടൈം എത്രയാണ്, അതാണ് ടി ഹാഫ് എന്ന് വെച്ച് നമ്മൾ റെപ്രസെന്റ് ചെയ്യുന്നത്. ഓക്കെ,
സോ സ്യൂഡോ ഫസ്റ്റ് ഓർഡർ റിയാക്ഷനിൽ ഒരു കാര്യം കൂടി നമുക്ക് പറയാനുണ്ട്. എക്സസ് ആയിട്ട് വരുന്ന റിയാക്ടന്റ്, വി ആർ നോട്ട് ടേക്കിംഗ് ദ കോൺസെൻട്രേഷൻ ഓഫ് ദാറ്റ്. In case in some reactions we have water molecules in excess. So it looks like they are first order, suppose, or second order. if more than one reactants are there. But in that case, we are not considering the excess quantity.
There is example is the hydrolysis of ethyl acetate. In hydrolysis of ethyl acetate, there is excess water. You will think that it's of higher order, but actually it is of first order. And other is inversion of cane sugar. That is also a pseudo first order reactant. These type of questions are frequently asked questions. Very important. Teachers question pseudo first order from this chapter. Okay. Now, this exam stress it will be more important. Okay, it will be more useful. Another question, explain why hydrogen and oxygen do not react at room temperature. And here is the answer. Hydrogen and oxygen do not react at room temperature because they do not have enough activation energy to overcome the exceptionally high activation energy barrier. Sangeeta Miss Ma'am activation energy is the minimum energy required to form the activator complex. So, this oxygen and hydrogen have a higher energy barrier. So, our energy barrier overcome activation energy at room temperature. They do not react at room temperature. Okay.
So, similarly, write the rate equation for the reaction A2 plus 3B2 gives 2C. So, this is the direct question. If the overall order of reaction is 0. So, here note down that according to the rate of a reaction, we can write rate is equal to dx by dt. Okay, that is the rate of change of the concentration of reactant. So here we are generally taking it as x. So here we are taking rate is equal to dx by dt, and since it is a zero order reaction, see, according to rate law, we can represent rate is equal to k into concentration of A raised to 0 into concentration of B raised to 0. So these powers are 0 because the order is 0. And see, anything raised to 0, we know that it is 1. So k into 1 is k itself. So we are getting rate constant as such. Okay. So I hope so far we have covered almost all the chapters, right? And this session I think was helpful to you. So just concentrate the question paper and the questions more asked questions. Okay. So I think we can wind up the session, ma'am.
Okay, do well in your exam. All the best.
All the best.
All the best.